So trends on your periodic table. So I think that the big ones you want to know about for your periodic trends would be your atomic radius, ionization energy. Do you want a blank one and you can label it now?
Well, I have like 3 blank ones. You have this, and then I label it.
That's a hard one to label.
I labeled in the shirt.
So I think that the atomic radius is the most important one to know.
Atomic radius corresponds with the whole intermolecular forces, right? And the what if it was like the ionization energy and taking away electrons depends on their shielding and all that.
Right. So all of the you have that whole concept is periodic trends. Like everything you just said there, that's all your periodic trends. So these are the kind of the big ones to think about, and then you're going to talk about how does your shielding and your nuclear charge come to play with both of those. So atomic radius is going to be your size of your atom. And since we can't actually like literally measure an atom, you're going to put these bonded together. And so it'll be the distance between the nucleus of one and the nucleus of the other. So you're going to compare those two. And so you'll just have to kind of sit them next to each other and measure it that way. Because there's no like defined outside of an atom. So it's kind of important to understand like the way the atom works. Ionization energy is going to be the amount of energy it takes to remove an electron. Whereas electron affinity is going to be the opposite of that. And so the amount, I skipped negativity, of energy released when we add an electron. Then electronegativity is the attraction for electrons within a bond. And polarizability has to do with how likely it is for something to become polar, which means they have an electron cloud distribution that is unbalanced. I'm going to say unevenly distributed electron cloud. So you're going to often be given equations for ionization energy and electron affinity. And then just have to kind of know that that's what they are. And so remember in your ionization energy that this is the process of adding, removing one electron. So if we're going to remove an electron, it has to be on the product side. And so let's say like bromine would always be the gaseous state. And remember what this looks like. So that would be one, but it's a bad example because it's not likely to show that. If it's going to become a negatively charged, or if it's going to lose an electron, it's more likely to be a metal. So like, let's imagine magnesium. And so remember, in ionization energy, it's to remove one electron. So this is going to become magnesium with a plus charge, just like the +1 charge. Now, likelihood is ionization energy for magnesium is going to lose 2 electrons. So you would see, like, you can also have the second ionization energy, is the idea that that first ion is going to lose another one and become magnesium +2. We could go on and say magnesium +2 loses another electron to become magnesium +3. And so one really common thing to ask about that question is, that's weird. I see you making a weird face. Like, why would this happen? Right, so we just went into another row. So we got to what we call the core electrons here. So to do this equation is going to require a ton of energy, lots of energy, as compared to these two, which would still require some energy, but a smaller quantity of energy, because these are valence electrons. And so my valence electrons are more readily removed because those are the ones that do the reacting. So our valence electrons versus our core electrons. And so one of the most common things to ask about is like identifying which ones are the ionization energy. And so I have these values, I haven't had them on my screen, 735 versus 1,445, and then 7,730. And this is kilojoules per mole for all of them. So you'll see these, it is always going to increase in the amount of energy because every time you remove an electron, it takes a little bit more energy to remove. And I want to talk about why that is here in a second. But you'll see here, there's a giant jump between the second and the third because that's where we get to those core electrons. And so you'd have to have some information if you wanted to pinpoint the specific element, but you would know this element has 2 electrons in the valence shell. And so you would guess that it's one of the alkaline earth metals. And then I can tell you it's the one in the 3rd row or the 4th row, and you can figure it out from there. So far, so good? Okay, and so then electron affinity is sort of the opposite. And so electron affinity is going to be something gaining its electrons. And so I was hoping I had like a good equation that had some units with it, but I don't. And so electron affinity would be any element, and it also has to be in the gaseous state, gaining an electron. And so now it's going to become negatively charged. And so now my X -1 still in the gas. And for some reason, I just always do it in the gaseous state. So this was, we were using the bromine. And so I figure you would really say it as 2 electrons become your bromine ion. Or we could use 1 bromine atom. That's just all you need to know about electron affinity. It's the amount of, so now some substances are going to lose energy, some substances are going to take energy in, depending on what's going on. That's a little different than ionization energy. For something that's more readily able to gain an electron, like bromine's more likely to take in an electron than release it. So it's more likely to release energy then when it's gained that electron. Just kind of remember when you put things together. Now it has a filled outer energy shell, and so it can move to that lower energy configuration, and it's going to release that extra energy. Whereas if it were like a lithium or magnesium, to add electrons, moving it to a higher energy configuration, and so you might need to add the energy that it needs for that. So electron affinity could gain or lose energy depending on the situation. Wouldn't expect you to necessarily come up with that on your own, but given an information like I said, this is the amount of energy that you would be able to explain it. So far, so good. Okay, so I got ahead of myself. We want to talk about shielding and nuclear charge. Do you remember what those words mean? And so anytime you have to do an explanation about anything relating to periodic trends, you want to use one or both of those words. So remember that your nuclear charge is going to be based on the number of protons. And so that's just going to be the positives that are in the center of your atom is going to dictate a lot of the way your atoms behave, because this is going to be how many positives charge you have, right? And so they're going to pull on all those electrons and keep the atom working the way that it is. Shielding comes from core electrons. And so this is going to be for every row or period of your core electrons. I'm going to say energy levels because that's the right word to use. And so we used that analogy of the coats. And so imagine it was winter and we went outside and you have one coat on. Your body is going to be shielded with only one coat. But if you put 5 coats on, you're going to be a lot warmer. And so you have more shielding. And so each coat represents your energy level. And so the more shields you have, the better protection there is from the cold, aka the valence electrons, to the nucleus, aka our body. Okay? And so we call that your effective, I left off the word nuclear, charge is going to be the combination of those two. How many protons do you have versus how many shields do you have? So it essentially tells you how that nucleus will affect those valence electrons. So when you're dealing with items that are in the same period on the periodic table, you're trying to compare within a period, you're probably going to be comparing based on their effective nuclear charge, because they're going to be in the same row, and so they'll have the same shielding. So that's going to be no different. So when we're dealing with a row of the periodic table, your explanation probably needs to include the words effective nuclear charge. If you're dealing with things within the same column or different rows, you're probably going to deal with shielding. So same row, effective nuclear charge, different rows, talk about shielding. Questions so far? Is this kind of what we were hoping for? We need to erase this. I'm running out of space. Let's talk about atomic radius, because if you can remember atomic radius, everything else base it on atomic radius. And so imagine if we have a periodic table. And remember, I can't stress this enough. In general chem, we expected you just to memorize. So the idea would be an AP that you have to explain. And so you have to know, imagine that I have a periodic table. It's not great, but you can imagine it, right? So my atomic radius, as we go down the table this way, gets the biggest as we move down the table. So this increase for atomic radius, remember, knowing that doesn't help you at all. Saying that is never going to get you your points. Explaining it is what's going to get your points. So the reason that we're going to increase in size is because we're going to increase in the number of energy levels. And so as your atom gets larger in size, it's going to increase your energy levels, and thus those electrons are further from the nucleus. And so we have decreased our effective nuclear charge due to an increase in shielding. So far, so good? Questions about that? Okay. So then if we go across the table, now we're going to assume that we're in the same period on a periodic table, the same row of a periodic table. Should draw my arrow the other way. It increases from the right to the left. It actually gets smaller on the right side and it's bigger on the left side. So you guys like it if, I don't know, you want me to say it decreases to the right? Huh? Just stick with increasing. Okay, so it increases right to left. And so the reason is because they're going to have the same amount of shielding, but so because you're increasing your shielding, I'm sorry, keeping your shielding the same, but you're increasing your number of protons, your effective nuclear charge will increase. So So that means every time I add an electron, I'm also adding a proton. And so since my shielding hasn't changed, that center nucleus has a greater charge and it pulls those electrons in more readily. And since it has a greater attraction, that causes my big atom to shrink down and become smaller in size. And so that's why it gets smaller as we move this side. So I'm going to have these tinier atoms. Ooh. And then this side, they're going to be really big. Because this one little electron doesn't have as great of a pull towards your center as all of these 8 electrons do towards the 8 extra positives in that middle when you're in the same row. Except what? Oh, like oxygen and nitrogen with those specific examples, exceptions. And now, so this would be things you would come up with on your own. Now, specific examples of, okay, so something weird has happened. We would expect nitrogen and oxygen, right? We would have expected that oxygen would be smaller. And I think that was in terms of ionization energy. I think it was ionization energy. We expected it to have a greater ionization energy, smaller ionization energy than nitrogen, but it actually had a greater ionization energy. And that's because nitrogen has a partially filled shell. That's a totally different conversation than what we're having here. So we're going to pause on that.
That was about how stable they were.
And so keep in mind that we don't want to use the word stability here because when we talk about stable, that's going to be like radioactive or not. Is it likely to explode? And so here we're going to talk about energy. It's all going to be in terms of energy. And so that in that instance, nitrogen, when it loses an electron, it's going to move to a higher energy level because it has partially filled shells. And that's where you have to know your electron configurations. And so this is S and this is P. How many electrons does nitrogen have? 5? Okay, just making sure I'm. And then oxygen has 6, right? So this would be nitrogens. And for nitrogen to have its ionization energy, it's going to lose one of those electrons, which causes it to go from this, where every box has its own electron. This is a lower energy configuration. This is going to be balanced lower energy configuration. When it loses that electron, now it moves to a higher energy configuration. It's going to take some energy for that to happen. Whereas oxygen, this would be oxygen's outer electrons. When it loses this electron, this is a higher energy and it loses that one. Now it moves to the lower energy. And so just being aware of the fact that having a half filled shell or a fully filled shell, apparently I've talked too much today, is going to be less energy or a lower energy configuration, which means that it's easier for an atom to maintain this configuration. It does not need to apply as much work to it than any other combination, with the exception of this. So being filled or half filled is ideal because it requires less energy on the atom's part. And if it's moving to that, it can give up that energy. If it's moving away from that, it's going to need the energy. Does that make sense? And that's for ionization energy, where we're talking about losing or gaining an electron. And remember, ionization energy has the opposite trend as atomic radius. So we had a side note. So speaking of things that are the same, atomic radius here and polarizability here have the same trend, because polarizability is going to deal with the size of your atom. The bigger it is, the easier it is to become distorted. So that's why atomic radius and polarizability have the same trend. The other three are the opposite. Your explanations and your reasoning is all the same, because here, as your atom gets bigger, those electrons are further from the nucleus and easier to remove. So they require less ionization energy, or they have less attraction within a bond, or they are going to have a smaller change in energy. So these all get smaller as you go down. These get more as you go down. So these are going to be the opposite. That's the opposite. Not very well, but that's what I was going for. So do you want to do some practice with periodic trends, or do you want to talk about PES and then come back to practice?
I kind of want to go to PES.
Okay. Is that okay? And then we can always come back. All right, so let's talk about PES. PES is how they figured out electron configurations. So they go together. Without knowing that, it's hard to understand how those electrons were able to be identified, because they're little. It's not like we could look at them. So your PES data. It's gonna be weird. I can like look at myself looking at myself. Yep, that's it. Okay, so this is a PES data. Put my pen in the drawer. That's a silly place for it to go. And so if you see here down here, it's got my energy values. And so just kind of watch that scale really closely, because it has the ability to change. Sometimes the highest energy is on the left. Sometimes it's on the right.
I didn't realize that's like the entire unit. That really messed me up.
Yeah, the different charts are different, and I've seen them use multiple different types of PES on the AP test. So I just like to prepare you for whatever. So just kind of evaluate yourself. The relative number of electrons will always be on the left. Your energy is always going to be on the bottom, but just kind of go from there and read your graph accordingly. So this one has an increase in the amount of energy as we move this way. So you then need to think about what we just talked about. Which electrons in my atom are going to have the greatest energy to remove? Take the most energy to remove. The ones closest to the nucleus or farthest from the nucleus? My core electrons. So this is going to take the most energy to remove. So that's probably in my 1s energy level. And then my relative number of electrons, well, it doesn't say so, but it's a pretty safe bet that each of these lines is going to represent 1 electron. So 0 electrons, 1 electron, 2 electrons. So I'm going to assume I have 2 electrons in my s orbital. We know it can hold up to 2, so it's either going to have 1 or 2. And so the fact that it's got 2 lines is a good sign this is going to have 2 electrons. And then after 1s, what's the next energy level after 1s? 2s. And there's 2 electrons again because it goes up 2 levels. And then after 2s is 2p. And this is where you have to kind of remember it goes SPDF. SPDF. Okay? So we don't have any Ds though until the second level. And you will have a periodic table. So you can always use that to help you remember. So here I have 1, 2, 3, 4, 5, 6 lines. So I'm going to get 2p6, which makes sense because that's how many electrons p can hold total. And so then this next one, what do we think it is? 3s, because I don't have any Ds in my second row. So then it means I'm done. I only have S and P. Then I'm going to go to S, and I've got 1, 2 electrons there. So it becomes 3s2. And now this one's going to be what? 3p, and then only 1 because I just have the 1 electron. So then we can figure out which element that is on the periodic table by going to the third row, and then in my P block, figuring out what that is. That would be aluminum. You're correct. My first element in that is aluminum. So then I identify this as being aluminum. In my electron configuration then would be 1s2, 2s2, 2p6, 3s2, 3p1. I remember what all we have to talk about. Okay, so when we compare 2 different elements, if we look at nitrogen versus fluorine, you can see the difference between the blue spikes are my fluorine and my pink spikes are my nitrogen. And if you see nitrogen versus fluorine on the periodic table, so I'm going to draw my little periodic table over here. So we've got fluorine is over here and nitrogen's there, right? And so since fluorine is going to be closer to the nucleus because it's smaller in size, because remember that it gets bigger as we move to the left. So fluorine is smaller, which means its electrons are closer to the nucleus, so it's going to require more energy to remove the same electrons from fluorine than it would from nitrogen. And so that's why when you're comparing your 2 elements, and that would be true then across the board because that fluorine's always smaller. Then you'll see here fluorine's relative peak went up 5, whereas nitrogen went up 2 because of their number of electrons. What other questions do we have about that? You had asked about Coulomb's law earlier. Remember, Coulomb's law tells us that things that have like charges, the 2 things that affect is the magnitude and the distance between your things. So like charges are going to be repelled, opposite charges are going to be attracted, and then it's just about like the greater the charge, the bigger the difference there will be. So they'll be more attracted or more repulsion. And then the closer they are together, the greater that difference will be. So the 2 things, just say that again. Magnitude of your charge, so like +1 versus +2, plus versus +3, or the distance between the 2. Electrons in fluorine are closer to the nucleus, so they have a greater attraction for each other. Coulomb's law was a big deal in this unit. What? You liked it? Oh, we've talked about, like today in class, we talked about coulombs, which is the amount of
6,485 or something.
Yep, that's how many coulombs it takes to transfer your electrons, and so.
What? You just do a lot. Maybe someday you'll do a lot person from the meeting after you. What kind of questions do they ask with like PES?
So the most common questions are probably going to be, what element is this? And just being able to pick it out. Like I've seen this, the most often it's come up has been on multiple choice so far. And so it's just, then can you pick out the right element? The only other thing, you know, like I guess a good question would be if I'd given you just nitrogen or just fluorine and then you figure out what the other one is based on the graph, or you could just give nitrogen and then be asked, so if I wanted to draw fluorines, would the spikes be to the left or to the right? And trying to explain that. Then the difference here between scandium and calcium. The idea here in scandium, you'll see that their one electron right there is going to be a little bit further to the right. And so if you figured out okay, this is a good one to look at because notice how, once again, my chart's changed, right? So this is stacking on top of each other because otherwise it would be super, super long. So this is 500, that's gonna be my greatest amount of energy, and that's 0.63, that's the least amount of energy. So this is gonna be my 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. And so that 3d1 is to the right of 4s2. So that's not the order that we filled them, but that is as far as electron energy goes. Remember, my 3d is closer to the nucleus than 4s. So removing the electrons takes more energy. And understanding that concept could for sure be something that came up on the AP test. Correct.
Could you, I guess this is something I got like, kind of confused with. It's like when you're writing out electron configuration, like 1s2, what are each of the like things in like 1s2 like represent? Like what is like the proper term like refer to that? It's like,
So 1 is going to be your energy level. The S, the P, the D, the F is typically referred to as your orbital. Sometimes it's referred to as your shell or your subshell, but orbital is probably the most common one. And then 2 is going to be your number of electrons. And that's going to, remember, be per orbital, because it's talking about how many are specific to S.
okay, which is like, I guess, which makes it easier to explain like the 4s2, 3d1 distinction because like obviously the 3 is the lower energy level.
Right.
Okay.
And as far as lower energy, you're thinking it's lower energy because it's literally lower in the atom, closer to the nucleus, which means it takes more energy to remove it.
Yes.
Okay. So what other questions do you guys have?
Mass.
Oh, yeah. I didn't write it on the board, so I forgot about it. Oh, I see. That was spectroscopy. I thought when you guys asked me that, you wanted to know PES, but you might have wanted to know this, and I was just confused. So mass spectroscopy, or spectrometry, excuse me, is when, this is where we had that we did the video and you watched like this diagram of the whole box, and they shot the atoms through this, essentially a box for whatever it is, and they had to turn the corner, and then they hit a shield. And depending on their mass, they hit at a different place on the shield, because if they're heavier, they're going to move slower. And if they're lighter, they're going to move faster. And so we used that concept. And then based on where they hit, we were able to measure what elements and how many things there are in there. And so then there's a lot of things we could do with this. Typically, we'll talk about it in terms of isotopes. And so we are told here that this is the spectrum for just one particular atom, atom Y, which is like an unknown atom. And so you can see they have the mass of 92, 94, 95, 96, 97, 99, and 100. So that's 1, 2, 3, 4, 5, 6, 7 isotopes that are available here for atom Y. So then this question, peak A and peak D come from atoms that have the same number of electrons. So we're looking for which statement would be false. If these all deal with atom Y, so each one is the same atom, would they have different number of electrons?
That would make them an ion. So
So atoms that came from the same, they're all atom Y, so they're not an ion, so they're going to have the same number of electrons. So this would be true. Atoms A and peak D have to come from atoms that have the same number of electrons because they are literally the same atom. Kirsten seems like she's not. Because they have, remember, isotopes can have the different number of neutrons.
oh yeah.
And electrons are very, very light, so they're not going to make a difference in your mass. So there are 7 isotopes of atom Y. Check. We just checked that and agreed. Peak C comes from the most abundant isotope. And so abundant would be how many you have. So your relative number of atoms, since this is the highest, that's going to be the most abundant. So that's also true. Peak D comes from an atom with 4 more protons than atom that gave peak B. And so peak D here versus peak B, their difference in mass is 4, but their number of protons has to be the same because your number of protons is the identity of your atom. The only thing that can change is your number of neutrons. So since they're both atom Y, they have to have the same number of protons. And so that's why that statement is false, making it the correct answer to choose for this. Then another good question for this would be like, what's the most likely atomic mass for this substance? And so when you're going to look at that, the one that's most abundant has the most weight in its, the most control of the average mass. Since we're talking about mass, it's hard to say weight, but like this is like how I weight your tests more than I weight your labs and much more than I weight your homework. Sorry. And so the idea that this C category is the one that's most abundant, so it has the most weight in its overall mass. So your average mass you would expect to be closest to 99.
And then that's how you do the second problem, right? You look at the,
Probably, yeah. You would look at the average mass and you would compare. I didn't read question. Yeah. So then we'd go to the periodic table and we would look to see which of those has a mass closest to 99, and that's where we would pick the answer from that. And I feel like zirconium was the answer, but I just am remembering that. And I think that of the choices, there weren't any ones that were close to 99 other than that one.
Oh my god. On the test, you get a periodic table that doesn't have the word like
Correct.
great. Am I gonna need to know where on earth zirconium is on this thing?
I mean, I guess
Oh boy.
zirconium's right here.
I'm gonna forget them in like 5 minutes.
Well, the nice thing about like zirconium, there's not very many elements that start with a Z. So you could probably take a guess. So there's like
That's true.
zinc and there's zirconium.
You would hope I would figure that out.
I mean, I would hope that you'd be like, okay, well, molybdenum, which I cannot say very well, has a mass of 96. And then americium.
oh, I always thought that was America.
Well, I mean, it is America, but, and so their mass is, its proton number is 95, but its mass is 943.
Oh.
And then einsteinium is 252.
I feel like I got really desperate for names towards the end of like, putting this thing together.
This thing, the periodic table.
Why are the Neptunium and the made up one?
Right.
Yeah, those like synthetically made ones.
So then the one with the most number of neutrons is going to be the one that has the most mass because they all have the same number of protons. So that's kind of the idea behind mass spectrometry. The only other thing I would maybe mention is this one is chlorine, and we knew chlorine was diatomic. And so we have 2 totally separate masses, right? It's all chlorine. So how come these are twice as much? Are those isotopes just that much bigger? No. but chlorine is diatomic. So these are going to be chlorines by themselves. And this is going to be chlorine bonded to another chlorine. And so it's just a combination of their isotopes together to form that. And so when you're trying to figure out how many isotopes, you would want to look at the ones that are just the individual chlorine atoms, because you're not sure how they combine together in this one, or if there's multiple ones that end up being the same mass. So you want to look at just these smaller ones.
And will the individual like atoms of a diatomic element always be like the taller ones to like?
No, not necessarily. Probably. Yeah. I mean, I would say yes,
Just make a
because.
grouping of the two.
Mhm.
Okay.
And then the other thing is they will have to be the smaller mass, though. That's the better way to look at it, because they're going to be just a singular atom instead of the double atoms. Okay. I feel like that's probably a good place to stop for now, because you have to get on the bus and you guys have been here till 4, and we can pick this up next week. Plus, we covered all your questions.
Thank you.
You're so welcome. Thank you for